This is a quick lecture on the brightness and luminosity of stars. These are the definitions and equations for each. Luminosity is the radiant energy per unit time emitted by a star. It's another name for the radiant power emitted by a star because power is energy per time. The variable is capital L and the unit is W watts. And the equation for luminosity is just the total radiant energy divided by the time. And when you think about it, the luminosity of any star is going to be a really gigantic number because the amount of power that stars put out in light every single second is really gigantic. Brightness is the radiant light energy per unit time delivered per unit area from a source of light. It's another name for the light intensity. So brightness is kind of like the observed amount of power that you're receiving at some given position away from the star per unit area that the light is impacting. The variable is lowercase b and the unit is watts per meter squared. The equation for brightness that we experience from a star is the brightness is equal to the luminosity of the star divided by 4 pi times the distance from the source, the star itself, squared. This may look familiar because this is actually a rewriting of the light intensity equation we talked about in the waves unit, and it means the same thing. It's the intensity equation applied only to light waves specifically. So the intensity equation for a wave can technically apply to any wave. The brightness equation is the exact same equation, it's just written with differently named variables just to talk about the brightness from light and the brightness from stars specifically. So if you're not sure why the equation looks the way that it does, I've linked the original lecture on intensity in the video description. So if you're not understanding where that 4 pi x squared comes from, it's basically because light radiates out in all directions in a sphere, and the equation for the area of a sphere is 4 pi times the radius squared. Again, if you're not understanding that, you can review the intensity lecture in the video description. Brightness is often called apparent brightness in problem solving because the value of brightness is determined by how far you are from the light source. So the brightness is always how that brightness appears to us. In astrophysics, we use the brightness equation to determine the distance to stars. We can only use this equation to determine the distance if we know the star's luminosity. So as an example, star A's luminosity is known to be 4 times 10 to the 31st watts if its brightness is observed to be 1.5 times 10 to the negative 7th watts per meter squared on Earth. How far away is the star? So we can just apply the brightness equation by writing down what we know. We know the brightness and we know the luminosity, and we're trying to find the distance to the star. And we can plug this into the equation. I'm just going to isolate distance because that's what we're looking for. When I isolate distance, I get distance is equal to the square root of the luminosity over 4 times pi times the brightness. And then actually plugging in the numbers gets me a distance of 4.6 times 10 to the 16th meters. So that's my answer to the problem, and that's how I apply the brightness equation to find the distance to stars. In example problem 2, star B is 9 times 10 to the 16th meters from Earth. How far from Earth would it have to be in order to be 1/3 as bright as it currently appears? This is a proportional reasoning problem, so I'm going to write an equation for the original distance. I know that that follows the same distance formula as I came up with before. The new distance to the star is going to have the same luminosity, but 1/3 of the brightness. So when I isolate my original equation in that new equation, I find that the new distance is equal to the square root of 3 times the original distance. So that means that to be only 1/3 as bright as it currently is, the star would have to be the square root of 3 times its distance away from where it is now. Plugging that into its original distance gives me a distance of 1.56 times 10 to the 17th meters away as compared to 9 times 10 to the 16th meters away. In problem 3, star A has an apparent brightness B. What would be its apparent brightness if it were 8 times as luminous and 5 times as far away? This is another proportional reasoning problem, so I'm going to write the equation for brightness and the new equation for brightness, plugging in the values. It's 8 times as luminous and 5 times as far away. Just carrying out that square and then isolating my original equation gives me that the star is now 8/25 as bright as it was originally. So that means that my answer is going to be 8/25 of the original brightness. So that's how you apply the brightness and luminosity equation on its own. In the next few lectures, we're going to learn how to use this to find the distance to specific stars given other properties of the stars.